When you think about a nuclear accident, your mind probably jumps straight to a meltdown, right? But what if I told you the thing that actually blew the Fukushima reactor buildings wide open wasn't the meltdown itself? It was something else, a hidden danger that was created during the accident. Let's dig into what that was. So let me just ask you this straight up. When you see those devastating pictures of the Fukushima Daiichi plant with the buildings torn to shreds, what do you think did that? Was it the earthquake, the massive tsunami, or the core meltdown we all heard about?
The real answer is both way simpler and honestly way more powerful. It was hydrogen. Yeah, the exact same element that fills party balloons and powers the sun. That's what did it. Those explosions that just ripped the roofs clean off those buildings were hydrogen explosions. And understanding why that happened is absolutely crucial to making nuclear power safer for everyone.
And those explosions, man, they were the absolute critical failure. They breached the final line of defense, something called the reactor containment. This is the ultimate safety barrier, the one thing that's supposed to keep all the dangerous stuff locked inside no matter what happens.
The best way to think about the containment building is like a modern fortress. It's this massive, super reinforced structure of steel and concrete. And its only job, its entire reason for existing, is to hold everything in during the absolute worst-case scenario. But at Fukushima, those hydrogen explosions shattered that fortress, and that's what turned a contained accident into a major environmental disaster. So the big question is, where did all this explosive gas even come from? I mean, a nuclear reactor isn't supposed to be a hydrogen factory, right? So how on earth does it get produced during an accident? Well, let's get into the science of it. It all happens in this simple but totally devastating chain reaction. Okay, so first, the reactor core loses its cooling and it starts to get incredibly hot. We're talking extreme temperatures here. At that point, the special zirconium alloy that covers the nuclear fuel rods begins to react with the superheated steam inside the reactor. Now, this chemical reaction basically rips oxygen atoms right off the water molecules, and what's left behind is pure, highly flammable hydrogen gas. And the amount of hydrogen we're talking about is just staggering. This is not some small, tiny leak. A big reactor can churn out over 1,000 kilograms of hydrogen gas. That is an insane amount of explosive fuel being pumped directly into a building that's supposed to be sealed and safe.
And here's where it gets even scarier. Once that hydrogen finds some oxygen, not all explosions are created equal. If the concentration is kind of low, you get what's called a deflagration. Think of it like a giant whoosh of fire. It creates a lot of pressure, for sure, but the building might just hold. But if that concentration climbs above about 10%, you're in the danger zone for a detonation. That's not a fire, that's a supersonic explosion. It creates a shockwave, like a massive hammer blow, that's powerful enough to shatter concrete and steel. It's literally the difference between a big fire and a bomb going off.
So how in the world do you fight a threat like that? Well, the strategy you use depends completely on the design of that fortress we talked about. See, not all nuclear reactors are built the same, and their containment designs have very different tricks up their sleeves for dealing with the hydrogen problem. Okay, let's look at the two most common designs out there. First, you have boiling water reactors, or BWRs. They do pretty much what the name says. They boil water right inside the reactor. This lets them be more compact, so they have a smaller containment building. Their main defense against hydrogen? They just get rid of the oxygen. The whole building is filled with inert nitrogen gas, so if hydrogen shows up, there's nothing for it to burn with. Simple, right? Then you have pressurized water reactors, or PWRs. They use a different system that requires a much bigger building. So their strategy is basically dilution. The inside of the containment is so massive that it's really, really hard for hydrogen to build up to those dangerous, explosive levels. Fukushima was, without a doubt, a massive wake-up call for the entire global nuclear industry. After that, countries all over the world went back to the drawing board and took a hard look at their hydrogen safety plans. It kicked off this huge worldwide effort to beef up these absolutely critical defenses. And what's really interesting is that there's no single magic bullet. You can see here, the US mostly sticks with inerting its BWRs. France, with its huge fleet of PWRs, relies on these cool devices called PARs to keep hydrogen levels down. Japan, having learned the hard way, went back and added PARs to its plants, and Germany uses a mix of different technologies. So every country really tailors its approach to its specific reactor. So what's actually in this engineer's toolkit?
Well, the real stars of the show are these things called passive autocatalytic recombiners, or PARs. They are brilliant. They don't need any electricity at all. They just use special materials to get hydrogen and oxygen to combine back into harmless water vapor. Then you've got igniters, which are basically like spark plugs that safely burn off hydrogen when it's still at low, manageable levels. You also have filtered vents to let pressure out without releasing radiation. And, of course, that strategy of filling the building with nitrogen we talked about.
Now, all those tools are fantastic for our existing reactors. But what about the next generation of nuclear power? Let's take a look at how new small modular reactors, or SMRs, are being designed from the ground up to stop this problem before it can even start. So for anyone who's not familiar, SMRs are a whole new class of nuclear reactor. As the name says, they're smaller. They can be built in a factory, and their biggest selling point is a major focus on what's called passive safety. That just means their safety systems rely on basic physics, things like gravity and natural air circulation, so they don't need any power or even a person to flip a switch to work. SMRs tackle the hydrogen problem right at the source. It's all about designing the problem right out of existence. Many have these passive cooling systems that make a core overheat, that very first step in the chain, way, way less likely. They're also being built with accident-tolerant fuels, swapping out that zirconium for advanced materials like silicon carbide that just don't make hydrogen when they overheat. And on top of all that, a smaller core just means there's less fuel to begin with. It's a total shift in philosophy, from managing an accident to preventing one from ever happening. They really are designed to be safer from the get-go.
So this is the really interesting part. How is all this global knowledge, everything from the tough lessons of Fukushima to these incredible innovations in SMRs, being put to use? For a fantastic case study, we can actually look at the incredible work being done right now in Indonesia.
What's so smart is that even before building its very first power plant, Indonesia's nuclear regulator, Bapeten, is already on top of this. They're proactively studying all these international strategies, and they're aligning with global standards from organizations like the IAEA. They're building the safety rulebook now to make sure any future reactors are built to the absolute highest modern safety standards.
And if you look at what Bapeten is focusing on, you can see they've really learned these lessons. Their new regulations are designed to cover all the bases we've been talking about, identifying every possible source of hydrogen, understanding the physics of detonation versus deflagration, setting crystal clear strength requirements for that containment fortress, and demanding specific systems to prevent and mitigate the threat. It's basically a complete blueprint for safety, right? From day one.
And really, this all brings us to the big final question. The hydrogen threat, it's a really serious engineering problem. But it's a problem that's being met with constant, brilliant innovation. From upgrading old plants to designing fundamentally safer new ones, the goal is pretty clear. So the question for us, as we look for clean energy solutions for the future, is can this relentless focus on engineering and safety finally get us to a point where nuclear power is truly fail-safe? What do you think?